In this video, we're going to talk about band reject passive RLC circuits, filters. We've talked about low pass filter, we've talked about high pass filter, we've talked about band pass filter, and this is the last kind of a core type filter. There's four. We've already talked about three of them, so band reject is the last core or basic type filter we're going to talk about. And as if you recall your band pass filter, this circuit looks very similar to the series RLC band pass filter, but in this case we're going to move where we are looking at. Our output would be across the L and the C, and if you do that, then our output basically will pass frequencies below omega C and will pass frequencies above omega C2, but it would block frequencies between omega C1 and in omega C2. Of course, omega C2 minus omega C1 is referred to as a band pass, for this filter. So, and of course, omega 0 is where you will have literally no impedance across here. So when that happens, this is going to be the lowest output you're going to see. So that's where almost everything is gone. And as we've talked about before, this is where H of S, magnitude of H of S, is 1 over square root of H of max. And since this is a passive device, this is equal to 1, which means at omega C, at the cutoff frequency, that thing is equal to 1 over square root of 2. And this is called the half power point. And we have two of them. We have omega C1 and omega C2 cutoff frequencies. So let's now walk through and see tactically how we go about doing that. We've done this a number of times, but let's go through it again. When we analyze a circuit like this, we use the knowledge we have from KVL, KCL, and all of that. We'll say, okay, this is the I of S that runs through this thing, and we're going to do a KVL around the loop, which basically says minus VI of S plus SL I of S plus 1 over SC I of S equal to 0, which basically says I of S is equal, we factor I of S out, is VI input S divided by S. Oh, by the way, just a reminder, S is really J omega, right? And then plus 1 over SC, which basically tells us that V out of S is just going to be IS times the total impedance here. So it's going to be VI of S times SL plus 1 over SC. And then, sorry, there's an R in here. I forgot to put it in here. There's an RIS that I forgot. And divided by SL plus 1 over SC plus R. Okay, so if that's the case, then we can take this V, bring it down here, and if you do that, then we'll end up with an equation that look like this. And now we have the transfer function for, transfer function for a band reject filter using a series RLC. So R, L, and C are all in series. Okay, so same as before, we can find the magnitude simply by finding the magnitude of the top and then finding the magnitude of the bottom, dividing it. We can find the angle by subtracting the numerator phase from the denominator, and then we go from there. Now let's go ahead and spend a little bit of time calculating the parameters. Omega 0, which is the natural frequency or center frequency, is equal to that. The definition of omega 0 though is omega C1, the first cutoff frequency, times the second cutoff frequency, square root of that. And as you can see, it happens, omega 0 happens when the impedance of the capacitor is equal to the impedance of inductor, so you've got a short, act like a short, the two of them together. Cutoff frequencies, as we've said before, this is the equation you use to find the cutoff frequency, the magnitude of h of s, when s is equal to j omega c equals to 1 over square root of h of max. Since this is a passive device, h of max is equal to 1 over square root of 2. To solve that, you end up with a quadratic equation, so there you have it. Now, since this is a band reject, so you will have two cutoff frequency. You have a bandwidth that you have to deal with, and the bandwidth is beta, represented by beta, is equal to that, and in a series filter, that is R over L. And then finally, we have quality factor as we've defined it in bandpass filter, is simply omega 0 over beta. And since we have beta, we have omega 0, we're done. Now, we could take this equation, we can either use this equation every time somebody asks us for a transfer function for a band reject filter. It's nicer if we were to calculate the beta first and the omega 0 first and then use this equation. And when I say nice, I mean it is an implementation independent, so when we go and implement it in different form, we still can use this equation as long as we calculate the beta for that implementation. The only thing that's implementation dependent at this point is the beta. And again, we also could find omega C1 and omega C2 as an implementation independence, because the Q's will change, beta and Q will change, but in the end of the day, these equations are the same regardless of how you've designed your band reject filter, active, passive, or otherwise. Another way we can do a band pass filter is to have the C and the R in parallel, and then we get the voltage across the R as the output voltage. We go through the process, solve it, and you notice that this equation is identical to the one we found for the series. The only thing that is different is that the the bandwidth beta is 1 over RC, where in this case was in this case was R over L. So that's the only difference between the two when you're actually trying to do the calculation for it. Also, if you recall, if these circuits are identical to what we had for band pass, the only difference is for a band reject, we are getting the output here for this one, where for a band pass, the output would be in here if you wanted to act like a band pass filter. Okay, and that same thing is true here as well. For band reject, we are getting the voltage here, but if we want a band pass, we'll get the voltage across here. So again, the band pass and band reject circuits are exactly the same. The only difference is where we are getting our output from.